Let's look at some more integrals. For the first integral, we get to utilize our knowledge of the derivative of the natural log. So when we look at this particular problem here, we want to write it in a more suggestive way. So let's write the ln of x plus 3 to the 1/2 power and then times the 1 over x. Now, of course, the derivative of ln of x plus 3 is 1 over x. So we have the u du, that is, we've got the power rule here. So that's a direct consequence of knowing the derivative of the natural log of x. So we add 1 divided by the new power, add 1 to 3/2, add 1 to 1/2, we get 3/2. Division by 3/2 gives us 2/3. So we have 2/3 ln of x plus 3 to the 3/2 power plus c. So we get a nice power rule problem knowing the derivative of the natural log. Now for the next problem, we want to write this in a suggestive way too. We have sine of 3x divided by 1 minus cosine 3x. So we're going to break it up. That is, we're going to think of 1 over u, 1 divided by 1 minus cosine 3x, and then the sine 3x here. But when we take the derivative of 1 minus cosine 3x, we get the positive 3 sine 3x because of the double negative. But we don't have the 3, so of course we put in the 3 and then we pay for it. Now we're table ready. That is, we have 1 over u du. So now we have 1/3 natural log of the absolute value of the u, which is 1 minus cosine 3x, plus an arbitrary constant. So this new integral form really gives us a lot of power, and this is a ubiquitous form. You see it in mathematics, physics, all the sciences, engineering. It's a very important form. Now here for number 3, we've got a definite integral, and it looks like a du, 1 over u du form. So what we're going to do is think of the 1 divided by 1 minus square root of x as the 1 over u, and then try to configure the 1 over square root of x as the du. But notice here, just like with the previous problem, the derivative of 1 minus the square root of x is going to be negative 1 over 2 root x. Okay, we have the root x, but we don't have the negative 1/2 power or the negative 1/2 factor. So just like we did up here, we'll put in the negative 1/2 that we need, and then we'll pay for it here. And now we're ready to go. We have 1 over u du. So now we have negative 2 natural log of the absolute value of the u, which is 1 minus the square root of x. But now we're good to go. We have our big F, just like we have a big F here, but now we have the limits of integration, so we need to use the fundamental theorem of calculus. So we factor the negative 2, and we evaluate our big F, or our antiderivative, at 1/4. So the square root of 1/4 gives us 1/2, so we have the natural logarithm of the absolute value of 1 minus 1/2, and then when we replace x with 0, we just get the natural log of 1. So we have negative 2 times the natural log of 1/2, 1 minus 1/2, giving us 1/2. And then, of course, the natural log of 1 is 0. We learned that back in college algebra. And so now we can use the power rule. The natural logarithm of 1/2 is just the negative log of 2, which we can replace here. We have two negatives, they absorb, so we have 2 log 2. So that's a very nice definite integral using our new du over u form. Now for the last one, I just wanted to throw in some miscellaneous, which I actually wrote up in your notes. And this is a really good problem because, again, you can look at it and think, well, I need to expand this, or what do I do? And this is where that miscellaneous technique is invaluable. So when you look at this, we kind of look in the denominator thinking that's where we need the substitution if we're going to have any hope of doing this. So we're going to let the u be x minus 4. This is where the u substitution is essential. In the first 3, it's trivial, straightforward integration, but this does require mapping into the u. So we have u is equal to x minus 4. Then, of course, du is equal to dx. So if we look up here, we need x, so we'll just add 4 to both sides, so x is u plus 4. And then, of course, we need x minus 8, so we can subtract 4 from both sides and get x minus 8 is equal to u minus 4. And now we just completely re-rig it in terms of u. So we have x which is what, u plus 4, and x minus 8, which is u minus 4. We get a difference of 2 squares, which is real convenient. And of course, the denominator is u cubed. So upstairs we get u squared minus 16, and then downstairs we have u cubed. Now we can break this up into 2 integrals that we can execute. So u squared over u cubed is 1 over u. And then, of course, for the second part, we get negative 16 times u to the negative 3. And I wrote this so we could easily apply the power rule. The 1 over u du is our new form. We just get the natural log of the absolute value of u. And here we just add 1 divided by the new power. So we get negative 2 divided by negative 2. The negatives absorb, and we have 16 over 2, which gives us an 8. And the u squared is downstairs. And now we just fill in u by its definition, x minus 4. So we have the natural log of the absolute value of x minus 4 plus 8 divided by x minus 4 quantity squared plus an arbitrary constant. So what we see here is that with the definition of the natural log, we have greatly expanded what antiderivatives we can compute, because before this, none of this was available to us. So we have a very rich number of new integrals that we can do, and we are done.